Hi, everyone. Really grateful for your attendance today with us. I'm going to be going over the code that was developed by myself, sorry, and my colleague Sabi Rousseau at the Center of Excellence for Exciting Science at the RMIT node in Australia. So this code is called PyPhotonics. PyPhotonics, you can guess, it's Python that does photonics stuff. Now, this code, this tutorial basically assumes that you have some background on Python, not necessarily very deep background, but just at least you can scratch the surface in Python, know how things go, variables, objects, methods, and that sort of stuff, and also know how to use VASP. So this tutorial is about explaining how to use the PyPhotonics code in order to calculate certain quantities that are based on VASP calculations. So first you do VASP calculations for your material, and then VASP is going to give you a few things, like some outputs. PyPhotonics helps you process this output and to compute some very relevant, some quantities that are very relevant to photonics. Okay, so just So the key thing here is photoluminescence. That's the domain that we are concerned with, and quantities that we are calculating are of relevance to photoluminescence. So we are calculating using VASP, calculating the properties of materials from which we can derive parameters that we can use in order to calculate the photoluminescence line shape. So photoluminescence, that's when a material emits light. So you excite the material, and then this excitation turns into emission, right? Now, the shape of the line, or the line shape of the photoluminescence when a material emits light, it looks like this. It looks like, you have the y-axis, which is the photoluminescence, the intensity of light that's emitted, and the x-axis, which is the photon energy of the light emitted. And the line shape here is how much intensity at every energy point. So if a material, for example, emits like red light, you're going to see a lot of intensity around the red light, whether it's the energy axis is in EV or nanometers. Now, how does photoluminescence happen? Many different processes. One of the processes that's the focus of this tutorial is defect-driven photoluminescence. You have a material, that's a diamond or boron nitride or whatever, and inside this material there's a defect, a point defect where a carbon is missing at a specific position, in diamond, for example. Or a boron is replaced by some other atom in your boron nitride. And these defects are involved in very interesting physics, in which the absorbed light turns into emitted light. So I'm going to be explaining this in some detail as we proceed. I just wanted to give an overview of what photoluminescence is about and why it's relevant to DFT calculations using VASP. So why this is very timely, why this tutorial is very timely, is because there are many papers that have increasing number of papers that publish the prediction of photoluminescence properties of defects in materials, but the code is not there. Has never been out there. So I thought, I've used my own code before to produce, to publish on photoluminescence properties in boron nitride in particular. And I thought, okay, how about we release it to the community in a way that people can use, can be easily installed, easily used in a accessible language such as Python, so that it can be of benefit to the community. And these are just examples of very recent papers published using, people have got their own PL, code and published papers. So you can see that these are really high quality works. And once you're able to perform the material science calculations using VASP, and then use PyPhotonics to process the output from VASP in order to predict the photoluminescence line shape, you might be able to, have, produce work like these. Okay, so let's just go back to theory. How is the photoluminescence line shape, calculated to start with? Photoluminescence is a phenomenon that involves light being absorbed by the material, and then after this absorption, excitation happens. So the material moves up into an excited state. So first it was a ground state, light makes it go to the excited state. But then when it goes to the excited state, a few things happen. It's not just that the electronic state of the material change, it's also that the geometric structure of the material changes. And I'm here talking about the geometric structure that changes in the vicinity of a defect. So let's say that you've got carbon defect in diamond, like let's say a missing carbon in diamond, and then that missing carbon, when it absorbs light, when light is emitted on that on that defect, it moves, it gets excited, right? And it's the energy of the entire system changes and moves up to an excited state energy. And when it does that, the geometry of the defect changes. So let's say that there was a carbon here bonded to another carbon and bonded to another carbon. The excitation phenomenon might be accompanied maybe by a change, in the structure, the geometric structure of the defect. The bond lengths might change, the angles might change, and so on. How can we capture such a change? We use a method that's based on constraint density functional theory, aka delta, SCF. People call it different names. And this has been documented in the paper that I published on PyPhotonics, which I'll show you soon. So we use this approach, which is supported in VASP, and actually not many DFT codes support the calculation, the SCF calculation. So VASP does support it, and I can, point you to a few references, including a reference I wrote on how to use VASP to do the DFT calculation. So we start with a ground state structure for the defect. We model that structure with VASP. So we optimize it. We obtain the total energy of that system, which is a ground state total energy. And then we compute the excited state structure and total energy. And these are going to be inputs for PyPhotonics. Okay. This mechanism, or this formalism that I'm describing here, has been developed over a long time. So people have been working on this since, like many, many decades. And one of the key papers in this field is the one by Jordan Markham here in Reviews of Modern Physics, I think in 1959. I don't exactly read it. And that's one of the key papers in the field. But the problem with it is that it was developed long ago. There wasn't, material science at that time was still, evolving. Later, many decades later, the group of Chris van der Wel, in 2016, they published a paper with a formalism to calculate the photoluminescence properties of material that borrows, or that is based on the formalism before it, or the developments before it, including that in this paper and many other papers. But what's cool about this work is that it is the formalism expressed here is quite, is very relevant in terms of the symbols or the mathematical notation. And also it's based on DFT, and they used VASP, right? So they published the photoluminescence line shape using VASP and using many flavors of VASP. So they compared the prediction of the photoluminescence line shape for a particularly interesting defect in diamond, which is a nitrogen defect in diamond, which is a negatively charged defect. And and they expressed the mathematical equations there. And they used VASP at the PBE level, and also at the HSE level. And obviously HSE, not really obviously, but might be expected that HSE was the most accurate in predicting the photoluminescence line shape. And also the Huang-Rhys factor. So the Huang-Rhys factor is another very important parameter in photonics, or in the in photoluminescence. If you don't know much about it, then you can have a look at the literature. It's based on a paper by Huang and Rhys, and it's a quantity that is a simplification for the electron-phonon coupling in the material. So electron-phonon coupling is the other thing, the other phenomenon that happens when a defect absorbs light. So remember, first I said a defect absorbs light, it moves to the excited state. This geometric change is accompanied with electron-phonon coupling. So electrons, the electronic states in that material during this transition from ground to excited, the electrons interact with the phonons of the material. And this interaction is, can be expressed in many different ways. There are very complex approaches to calculate the electron-phonon coupling. And you might need the complex approaches if you need high precision values for the electron-phonon coupling, such as in superconductivity. However, in the case here, we only need rough estimates for the electron-phonon coupling. And we're dealing with materials with very large supercells, so we cannot really afford high quality calculations of the electron-phonon coupling. And therefore, we use simplifications, including the simplification that was adopted by Huang and Rhys. And that's why it's called the Huang-Rhys factor. Okay, so that's the paper I mentioned, the 2016 paper by the Chris Van de Waal group. They used VASP. They used their own code to calculate the PL line shape. And as you can see here, the experimental line shape for the NV defect in diamond, which is the that one here, that curve here, nearly overlaps with the blue curve, which is the HSE calculation using VASP, right? So there is big promise in using the formalism that is based on the Huang-Rhys, and that has been adopted by this group, by the Chris Van de Waal group. Huge promise in using it in order to predict the photoluminescence properties of defects. And that was the key motivation. I used that approach in order to study photoluminescence line shape and photoluminescence properties of defects in hexagonal boron nitrides, which were discovered in 2016 by a group in the University of Technology, Sydney. And we produced this paper together. And later I worked with another group, University of Sydney, who produced this work on sub-Bosonian photon emission. So in these two works, I used code, that is, earlier versions of PyPhotonics in order to study defects. And in particular, in that first paper, the nanoscale paper, this was the key output. So I had photoluminescence properties of hexagonal boron nitride defects at 4 Kelvin, and that's the that's the black line here. And then using VASP plus code that I developed, the field line shape was, that's the field line shape, which is not overlapping with the experimental line shape, but at least it qualitatively agrees with it. So yeah, and that, of course, in order to find a defect that agrees with the reported experimental defect, we had to go through like 35 defects, and we had to calculate several quantities in order to filter down those 35 defects to 3 defects. And these quantities are the ZPL and the delta Q. These are very important quantities, and I'm going to be discussing them as we go. So PyPhotonics now is free, available. It's Python, it's on GitHub. You can very, very easily install it. Only requires basic Python experience, but requires that you know a lot of, you know how to do VASP, and you know how to do VASP phonon calculations as well. Okay, and that's the reference, the key reference paper published in CPC on using, on PyPhotonics. So all the mathematical formalism the equations are all there, as well as some theoretical background for you to know what's, to understand the formalism in its context. Okay. So if you want to go and have a look at PyPhotonics, it's on GitHub in this link, right? And it's so easy to download. All you need to do is just you go to your command line and pip install PyPhotonics. Boom, you got it. And the packages that are needed by PyPhotonics are only those 4 ones. Obviously, it's IP, NumPy, and pandas for data processing and mathematics, and matplotlib because you're able to install, you're able to plot the PL line shape using PyPhotonics. Okay, let me explain the workflow. I'm going into the technical details of the know-how, how to use the code before I delve deeper into the details of what is calculated. Because I know that this might be more urgent to people here. They want to know how to use it first, and then, okay, what can it give us? If you want to know what it can give you, then I just gave a brief overview, but then I'll get into more details after I'm done with this workflow. So the first thing you need to do is identify your defect. You have a material, let's say silicon carbide, diamond, boron nitride, or any other perovskite, or any other material. You need to identify a defect, and that's most probably something that you already worked on, and you're interested in a specific defect in that material. After you identify the defect in the material, you need to do geometry optimization of the material structure, right? Including the defect. So you build the material large enough, so the supercell has to be large enough in order to ensure that the defect inside it does not communicate with or does not couple with that image of that defect in the other images of the supercell, and perform a geometry optimization. If the supercell is too small, you're going to get wrong results, right? Because defect coupling changes the total energy, might induce problems related to having a charge and a charge, and a Coulomb interaction between them, raising the energy unnecessarily. You need to space between them as much as you can. You can do this, in diamond, for example. I think 7x7x7 supercell is enough to have nearly accurate prediction for the photoluminescence properties of a single atom defect inside that box. That's basically a 2x2x2 supercell of diamond. Similar thing applies to other materials. And I've tested myself. People have contacted me with regards to using PyPhotonics, and it appears that that's the range of supercells that is meaningful and that can deliver reasonably accurate photoluminescence properties. So again, lattice and structure optimization for the ground state. The next step is structure optimization for the excited state. So we keep the lattice in the ground state and we just perform optimization in the excited state. And as I said earlier, that is when you invoke CDFT, constrained DFT, or delta S DFT. So in constrained DFT, you constrain the occupation of your electronic structure to a particular occupation. Most probably it's going to be a HOMO-LUMO occupation, so a transition, or like an occupation where the HOMO electron is moved and kept at the position of the LUMO electron, and you optimize the system in that way. This is going to give you a structure and a total energy different from the ground state. That is just an approximation, or a reasonable approximation for the excited state, energy and structure. If you are studying defects that emit very narrow, light in a very narrow range of frequencies, and let's say maybe single photons of light, you're expecting that the change in the energy, the change in the geometry is not going to be significant, only small or minor change in the geometry. That change in the geometry from the ground to the excited state That is what we call here the delta Q. So that's the delta Q here. It's a quantity that is calculated by summing the change in all the coordinates from ground to excited state, and the change in the total energy from the ground to the excited state, that is the ZPL. So the ZPL and the delta Q are both two quantities that are calculated in the PyPhotonics code. Okay, so we got these two now. So we have the lattice structure, we have the optimization for the excited states. While running your CDFT to optimize the excited state, you can actually start doing the phonon calculations. We don't need to do phonon calculations for the excited state. We just need to do phonon calculations for the ground state in most cases. So we take the ground state geometry, we do the phonon calculations. Now, how do we do the phonon calculations? We just basically resort to the simplest way to do it. You know, there are two ways to do phonons in VASP. You either do finite difference phonon calculations, or you do DFTP with perturbation theory. There's a functional perturbation theory, DFPT, sorry. Now, these two methods, most cases, they deliver similar phonon results, so similar outcome for the phonons, such as vibration density states. The energies of each of the phonons are usually the same or close. But what I found is that the first method, which is the finite difference method, which is supported also in phonopy Python code, it's very, very quick. So you can very, very quickly calculate the entire phonons, the phonons for a defect if you go with finite difference method. Now, how do we do finite? If you haven't done it before, how do we use phonopy to calculate the finite difference? Use finite difference to calculate phonons. I've got here a link. I'll just show you the page. So that's VASP and phonopy calculation page in phonopy website here. So I'll also put it in the chat if you're interested. Chat. So that page here helps you set up a phonon calculations using phonopy. And what phonopy needs at the end, in the beginning, it just needs from you to provide a postcard file for your ground state equilibrium geometry, and make sure that that ground state geometry is optimized, both atomic positions as well as lattice. Because when you're doing phonon calculations, the lattice must be the minimum energy lattice. If it's strained, this is going to affect the vibrational properties, might introduce imaginary frequencies. You don't want that here. So the first step is to use phonopy to generate postcard files, right? With displacements. That's why it's called finite difference. The finite difference method is based on getting a lot of displaced calculations, displaced atom calculations, and then calculating the force constants based on that. So the first step is produce all the postcards that you need, use those postcards into fresh new single point VASP calculations. So if you have, like, let's say, one structure that requires 200 phonon calculations, you can, after the step, produce all the postcards, write some Python, generate the VASP folders as inputs. Each folder is going to be a single point VASP calculation, not an optimization, just a single point. So you fix the geometry, you fix the lattice, and you just run a single point calculation to obtain the forces on the atoms, right? And of course, if you have 200 or even 1,000, VASP, single point VASP calculations, you can just, and you're sitting on a supercomputer, you can submit all of those at once, and a supercomputer can calculate, all the single point forces very, very quickly, because each one might take, for a small supercell, let's say 50 or 60 atoms. Yeah, for 60 atoms, for example, it might take like 10 minutes per calculation. So you can have, within an hour, you have all the phonons calculated. But of course, this depends on the size of the supercell. Diamond 4x4 it takes a lot of time. So using VASP to calculate the single point phonons for every displacement took from me, I think, more than an hour. So I think there were like 400 of those. So, that's very expensive calculation. However, a nice colleague, I think from Europe, contacted me sometime earlier and told me that he applied the PyPhotonics after performing not a single point, but performing DFPT, density function perturbation theory, calculations for the vibrational spectrum of a 4x4x4 diamond, and that his results agreed with the literature results on the same sized supercell of diamond, which was great. But I'm sure he has gone through more agony because DFPT on such a larger supercell is tremendously more expensive. But anyway, I mean, thanks to him. I thanked him in email. I'm thanking him again here for doing this, confirming that PyPhotonics reproduces the literature for different sizes of supercells. Okay, so after you generate the postcards and you do the individual single point VASP calculations, which are these two steps here, you get phonopy to process the VASP output. So what phonopy is going to be asking for here is the VASP XML file, which VASP leaves in its directory, in the calculation directory, and then phonopy is going to produce band.yml. So that is the file. That's really the only file out of this entire process that PyPhotonics is going to look for. Eventually, PyPhotonics needs the band.yml, the band.yml file from phonopy, the quantcar for the ground state from here, the quantcar from the excited state, and that's it. That's all what it needs. Once it has those, then it can produce its outputs. So let me give you, so that's a code example here of the steps. So first you import photoluminescence from PyPhotonics. And that example is for a 2x2x2 supercell in diamond. That's in particular, that's the nitrogen defect, vacancy defect in diamond. There are 189 phonon modes available in this defect. M here, that's a list of atomic masses. So we have like 63 carbons and 1 nitrogen. I'm going to go to the Python code. We have a closer look. You identify the path for phonopy and for the phonopy file, phonopy bands.yml file, and the path for the structure files, the quantcars, for the ground state and excited state, and then create a new object, photoluminescence object, and that object is going to be doing all the calculations for you, and then you can use it to produce your figures. Okay, so before I move on, yeah, so that's the results of this code. This code can generate for you the partial Huang-Rhys or the partial HR function, and which is the basis for calculating the PL line shape. And that PL line shape here resembles to a great extent, the actual PL line shape for diamond, for the NV defect in diamond. Let me quickly show you here in the PyPhotonics GitHub. Here's the test folder. And so quantcar ES, that's the excited state, quantcar GS, the ground state, and diamond, right? So diamond.py, that is the sample Python file that shows you how to use PyPhotonics, for diamond defect. Yeah, so there are 63 atoms in that defect. The first 62 are carbon and 1 is nitrogen. It's a negatively charged defect, remember? So when you're calculating the electronic optimizing a defect that is charged, you know what to do here. Use the nelect tag in VASP to specify the number of electrons. Likewise, in the CDFT calculations with VASP. And then you invoke the photoluminescence object here on these inputs. So that's the phonopy path that leads to the bands, YAML, and it's actually here as well. What did I do? Yeah, phonopy. That's the band of YML here. Let's go back here. And then once this is done, we can obtain delta R, delta Q. Delta Q is the quantity I told you about. That is an indication of the extent of geometric change after absorbing light. And the Huang-Rhys factor is right here. So these quantities are all calculated using PyPhotonics. Once you instantiate an object, the photoluminescence object, and then in addition to that, you can plot a figure of the partial HR function, the S omega function, and to plot the PL, first you need to call the PL method from photoluminescence object and specify a few parameters, and then you can plot it here as you can see here. So this test is has got all the necessary inputs in order to obtain the outputs in the paper, and also the ones I showed you in the tutorial. So that's the photoluminescence line shape of the NV defect in diamond. And yeah, so that really concludes this tutorial. I hope I was able to provide you with some information on how, and some help on how to install and use PyPhotonics. And I hope this was clear enough to you, and I'm more than happy to receive questions from you if you have any questions now, or if you have any questions after the tutorial. And as Nikki said at the start of the tutorial, the YouTube of this tutorial is going to be also posted at the Exciting Science website, sorry, at the Exciting Science YouTube channel. Thank you everyone, and thanks, Nikki.
Thanks very much, Sherif. That's great. Thank you. I hope that proved useful for everyone. We'll just give it 1 or 2 moments in case people are thinking of a question or typing a question, and we don't want to miss that. So yeah, let's hang on for 1 moment. But otherwise, we should also mention, I'm just navigating my mouse up to my other screen here, that we have another tutorial at this time next Wednesday, which is about rapid ab initio one-shot descriptors for machine learning. Sherif, did you want to say anything about that tutorial for this audience, just in case there's some crossover? Or
yeah, sure. So the next tutorial about the ROSA descriptors, the one that about developing new descriptors that are somewhere between complex ab initio descriptors and simple geometry and atomic based descriptors. And Python code in order to generate those descriptors from materials, and using those descriptors to train machine learning models to predict the band gap and the formation energy. So yeah, please, we'll be really pleased to have you with us next week.
Great. I've just posted a link to that tutorial on our events page, where you can find the Zoom registration link. So yeah, we don't have any questions from this one, Sherif, so it must be so exhaustive that no one could have any doubts or any uncertainty remaining.
I hope so.
Oh, actually, sorry, we do have one question in the Q&A.
Yep.
Let's answer it live. So can you see that question at your end as well, Sherif?
Yeah. So the mass part here, that's just an array. Let's go back to the code here. So that mass.
Sherif, would you be able to read the question out just so the video recording?
Yeah, sure.
If people are watching later.
Yeah. So thanks, Manoj, for the question. Can you explain about how to select mass part by taking another example? Let's say C defect in gallium nitride. Okay. So in gallium nitride, carbon defects, right? Let's say that your gallium nitride, there are 100 atoms. There are 50 gallium and 50 nitrogen and 1 carbon. Your postcard is going to organize those atoms in that way, possibly like 50 gallium, 50 nitrogen, and 1 carbon. So the way to organize your that array, the mass array is exactly as the same order as your postcard. So you would fill the array 50 up to 50 with a gallium mass, and then multiply it by this quantity in order to convert it to kilograms. And then another 50 for the nitrogen, which is that number, and then 1 for the carbon. That's it. I hope that was easy.
Hopefully that answers the question, Manoj. And would I be right in saying, Sherif, that if anyone is watching this back later or having a think about it and they get stuck, then you might be able to help them with some of those questions?
Yeah, sure.
And actually, yeah, great. So Manoj said, thank you very much. We also have another question. Would you be able to have a look at that one for us, Sherif, and read that out as well?
Yeah, is it possible to calculate the line shape of organic small molecules? Now, molecules is a different thing. There are actually, I think there are codes that do, PL for molecules, but PyPhotonics is for crystal structures, and it's been developed with that in mind. So molecules is not one of the application areas. I'm sorry, unless your molecule sits in a crystal structure. And being in a crystallized form is important for its PL properties, but otherwise, yeah, I wouldn't advise you to use PyPhotonics for molecules.